All right. Well, first of all, Aggie, thank you very much for coming by tonight. It's great to have you.
You're welcome. Thank you for having me. Yeah, I really appreciate it. I actually love, okay, I'm not going to say this. Obviously, like the pandemic is horrible. I don't love the pandemic. But I love that since it's happened, there's been so many talks online and I just have access to all of these amazing talks and I get to give talks at all of these like amazing places and meet all these people. So it's super cool. I hope when things go back to normal, we don't lose this aspect. It would be sad if suddenly all of the talks are going to be, just local again and we don't get to share them.
Well,
So,
yeah, yeah, it'd be interesting to see what happens. I think the benefit is we can talk to you from Waterloo. In meetups are supposed to be in person. That's the meetup.com thing.
yeah.
But the beauty is we can get folks like you because we've got George who's on the line here somewhere in Philadelphia, so we get him to speak. But we can't get him to speak every month, right? Because Philadelphia is not that big of a market. So yeah. I mean, COVID is a big win, and Jamie's I think Jamie's in Wisconsin, and so
Jamie Gill.
Yeah, Jamie Gill. Everybody knows.
Yeah, we met at these Women in Quantum events, actually.
Yeah. He's at every meetup there is. He I think he subscribes to Quantumopalooza. I see him sometimes 4 times a day, literally 4 times a day sometimes, and there's some others.
That's amazing.
Like that. Yeah, I'm trying to get him to give a talk, but
well, he should.
Thank you. He should. All right, sorry. I'll shut up.
Are you seeing my main slide? Is that?
Yep. Everything looks good technically. All yours. Thank you.
Okay, cool. Yeah. So thank you very much, Terrell, for having me, and thank you guys for coming. All right. So actually, my first slide is a map, just so that we can get some context for where we are. So the meeting is supposed to be in Philadelphia, but where's Harrisburg, Terrell? You said it's west, like.
It's about, see that yellow line where your cursor is?
Where the traffic is?
Yeah, go west. The yellow, no, west, not south.
I don't know.
Optics people.
That way?
Yeah, west, left.
I don't know. I'm from Australia. It's all backwards.
Yeah, that's true.
I'm going left.
Okay.
Oh, like this.
Right where you are.
Anyway, we won't waste time on this.
Knowing where Harrisburg is important.
Anyway,
go ahead. Sorry.
Yeah. So yeah, it's like 8 hours drive, which means probably after the pandemic, I can come visit. I don't know why it's a 22-hour flight. Maybe that's.
I know why.
That's normal, but that's is it the pandemic?
Yeah, I think so.
Okay. Anyway, let's talk about some physics. Yeah. Okay. So this talk, it's about quantum light. And so I wanted to, I think quantum light is like really interesting in its own right, but I wanted to motivate it from an applications perspective as well. So one of the common applications that you will hear about is to do with quantum information applications. So if you were wanting to build a quantum computer out of light, you could, for example, encode your qubits into photons. Or if you were building a quantum computer out of something else, like superconducting qubits, then you would still need quantum light to connect the different qubits in different parts of the lab. Quantum light is really great, easy to send from one place to another because it's light, and so it's you can use it to send share quantum keys, quantum cryptographic keys between satellites and so on. Away from the quantum information perspective, there's also other applications like you can use quantum light to enhance spectroscopy or metrology. For example, this is a picture of the LIGO interferometer. It also has a lot of application in testing foundational physics. So in particular in a lot of quantum foundations experiments like the famous Bell experiments. And it's also possible to use it to model analog experiments. And so I'm super excited to mention this one today because this is a paper by my PhD student Eugene Aggie and our collaborator Kevin Resch from the Institute of Quantum Computing. We published this paper today on using nonlinear quantum optics as an analog for this super cool effect called the Unruh effect. So lots of applications. So in this talk, I wanted to cover three things. I wanted to first just briefly describe quantum light, or just light, and how we model it, so both the quantum and classical side. And then I wanted to introduce the Wigner function and tell you about some interesting features of it. And finally, I was going to say a few words about how to actually make these states of light. So this is the new part that I didn't have at the previous talk. Okay, so what should you get out of it? Well, hopefully you will become more familiar with the common states of light. And hopefully next time you see a paper or a talk showing a Wigner function, then you'll probably get what they're trying to communicate. And you'll also have some idea about how different kinds of quantum light are made in the lab. So let's start with our, it should be called descriptions of light, not toy models. But anyway. So I'm sure you've noticed around you that there are many different kinds of light, such as sunlight, light bulbs, lightning, candlelight, lasers, and neon lights, and so on. And so these are all, you can think of them as classical states of light. But when it comes to quantum light, we also have several different kinds. And since they're probably going to be not entirely familiar to you, or at least not all of them will be familiar, I just wanted to take this slide to show all of the different kinds that I'm going to talk about, just so that you have like a bit of a big picture. So yeah, the kind of most basic state of light that you see in quantum optics, it's called a coherent state of light. It usually is the state of light that we use to represent what comes out of a laser. We also have squeeze states. So these states are, they're useful for enhanced metrology, like in the LIGO interferometer that I showed before. You may have heard about something called a Schrödinger cat state outside of the context of quantum optics, but we also have optical Schrödinger cat states, so I'll mention those later as well. We also have probably the most fundamental states in quantum optics, and these are called photon number states. So I like to think of them as buckets that are populated with different numbers of photons. The reason I kind of think about it in terms of these buckets, because two photons that populate the same quantum state are fundamentally different than two photons that populate different quantum states. So I think of the buckets as representing a quantum state populated by some number of photons. And finally, you can have a quantum state with nothing in it. And so this is known as the quantum vacuum state. And what's special about the photon numbers is that you can add them together in a coherent way. So you can take a superposition of these photon number states. And if you pick the coefficients, like the weightings the right way and the phases in the superposition, you can actually make like any of these other interesting states of light. And in fact, you can make like any quantum state of light that you can think of. So the technical term for that is that they form a basis for the states of quantum light. Okay, so light can have many properties. You know, it can have color, intensity, direction, polarization, phase. It can be pulsed or it can be continuous. It can be broadband or narrowband. It can be coherent or incoherent. And so all of those things apply for both classical and quantum light. But quantum light has some additional properties that classical light doesn't have. So some examples of this are the photon number, which I already mentioned. Also this notion of squeezing, which I mentioned. Quantum noise, which I'll talk about a little bit later. And also this idea of entanglement, which we won't really cover in this talk, but it's a fundamental property of quantum light. And so, you know, in principle, we have equations that can model all of these properties, but in practice, it's very challenging to get solutions. The solutions are very complicated and take up, you know, a lot of computational power to solve. And so usually what we do is we focus on just a few relevant properties and just, you know, use simplified models to model what we're interested in. So what I'm going to do, like in the next couple of slides, is to just start with a really basic toy model for classical light, which I'm sure you'll be familiar with. And I'll kind of build up on top of that into a slightly different model, which maybe you haven't seen, which I will then convert into a quantum model. Okay, so let's start with, the classical one. So I'm sure you're very familiar with the fact that light can be thought of as a wave. And mathematically, we can represent a wave as a sine wave. So here we have this sine wave. And this is, so we've simplified it. We've said that we only have a single color. So we have a single frequency of this oscillation, single polarization, single direction, and so on. And once we've picked all of those, fixed all of those parameters, we're only left with two important parameters that we can vary. And so these parameters are this amplitude here, so the A, and this parameter phi. So the amplitude is, it's how high these oscillations are, and it's related to how intense the light is. So if the light is more intense, then you have a bigger amplitude. The phase is it's how much this wave is shifted from left to right. And this is important because the phase tells us how two waves are going to interfere. It tells us if we have constructive interference or destructive interference. So these are important parameters. So, okay, these are our amplitude, which is going to range from 0 to infinity, and our phase, which ranges from 0 to 2 pi, because it repeats. Okay, so anytime you have some kind of state that can be described by these two parameters, you can actually plot it on something known as a phase space diagram. So here I have two axes, which you can just think of as Cartesian coordinates. And then, I have a point here, which represents the state of light. So if the point is close to the origin, that means it's low amplitude. And in fact, if it's on the origin, its amplitude is 0. So, high intensity or high amplitude light is here, low intensity is here. And the phase, so how it rotates from this axis, tells you how it's going to interfere. So for the rest of the talk, I'm going to focus on this phase space picture rather than this light field picture. So maybe this is a good point to just stop and see if anyone has any questions about that transition, so that you can be kind of sure you can follow the rest of it.
I've got one, if I may.
Okay, yeah, I'd love one.
So minus A amplitude, you don't have negative A on the phase space diagram.
Yeah.
So is that shifted accordingly, or how do they map to one
No,
another?
so A is the parameter, and then the plus A and minus A are just kind of, I'm just labeling the axes, kind of the point in the axis, but there actually is no minus A. Like if you, if you had, let's say if you had an amplitude, well, it physically doesn't really make sense, but maybe, oh, no, maybe it does. Okay, if you had a minus A, what that would be equivalent to is just flipping this, this light on the x-axis. So yeah, so minus A is the same as A with a phase shift of pi, which actually makes sense because e to the I pi is minus 1. Mm-hmm. So yeah, so in fact then, like I would have had to draw this diagram a bit better to have space on the other side, but a minus A amplitude would be kind of on the other.
Oh, right. Yeah, okay. Yeah, because the angle there could be, over like 185 or minus.
Yeah, exactly.
Whatever.
Yeah, so it would be like minus A would be like an angle of phi plus pi, which would like go all the way around here and then all off the screen.
So A in the phase space diagram is really kind of like so if the amplitude is 10, plus or minus 10 in the light field picture, the A in the phase space diagram would be 10 or 20?
The A would be 10.
10, okay.
Yeah. And then actually, so
Right.
there's a relationship
okay.
between the amplitude and the intensity. So I think it's like mod squared. So if I mean, okay, you'd have to like play around with constants and the units and stuff, but to get a feel for it, if your amplitude was 10, then your intensity would be 100 because it's 10 squared.
Okay.
If it was minus 10, your intensity would still be 100 because minus 10 squared is 100. So your intensity doesn't really, it can't tell much about the phase. It doesn't see the phase. It only kind of depends on the absolute value.
Shital asked, go ahead, I'm sorry.
No, go ahead.
Yeah, Shital, if I say that correctly, said modulus A. What about wavelength? How does that play?
So wavelength, so in the light field picture, the wavelength would just compress these oscillations or spread them out, but you have to fix the wavelength. You have to choose, some particular wavelength before you move to the phase space picture. So you could have two different, phase space pictures with the same A and same phi representing different wavelengths.
Okay.
But you that wouldn't be captured in the phase space diagram. You would have to put a little note on there saying this represents green light or this represents blue light. It's kind of some additional feature that's not in the phase space diagram. So the phase space diagram already assumes everything else is fixed.
Okay. Yeah, we've lost that information in the phase space piece.
Exactly.
Yeah. Okay.
Exactly.
Thank you, Shita. Okay.
Okay. So if we're cool on phase space, let's move on. Okay, so now we've got the classical picture, which was just a point in phase space, and we're about to go quantum. So if we look at the quantum equivalent of this kind of state, rather than being a single point in phase space, it's going to be this blob. And so this blob represents this idea of quantum noise. Or quantum uncertainty, which is something that's very inherent to quantum light. And so, I mean, in some sense, I can kind of schematically represent it as this coherent state. So, this is our wave picture that we saw before, but now it's got some uncertainty. It's got some kind of fuzziness, which is the quantum noise.
Can I interrupt with a side question?
Yeah.
So what is 7:30 plus 9.5 hours? Does anybody know? 7:30 p.m. plus 9.5 hours.
You think it's going to take 9.5 hours?
No, Syed from India just popped up as your audience, and I'm calculating, is it 4 a.m. or is it 3 a.m.?
It's almost 5 a.m. here.
5 a.m. Okay, I was off a little bit. Welcome.
So the question is, did you just wake up or are you still awake?
Oh, I just woke up.
Okay. Oh, that's impressive.
Yeah, I had set my alarm for this talk.
Oh, well, that's great. Well, you have to ask some questions. Otherwise, it's a wasted opportunity because you could just watch it online later.
Exactly.
Yeah, sure. I'll ask a few questions.
Excellent.
I thought you were saying like +9, meaning that this talk is going to take 9 hours. I'm like, oh my God.
I had more info, and we got 7:30 in Australia. Look at this. Boy, you're waking people up.
Oh, sorry. Okay, so shall we go on? Yes. Okay.
Yeah, unless somebody's here from Beijing or something.
So yeah, so we've seen that we can go from a single point in the classical picture to a blob in the quantum picture. And so I mean, I'm kind of like just saying this in the hand wavy way, but there's a way to motivate it more concretely as well. But we're not going to do that here. Okay, so what's interesting about that is if I look at a state of light that has 0 amplitude, so it's going to be right here in the middle, classically it means there's nothing there. It's just nothing. But quantum mechanically, even though the blob is centered in the center, it has some quantum noise, it has some uncertainty. So quantum mechanically, the vacuum, emptiness, is not really empty. It's got some energy associated with this quantum noise. So that's something that is unique to quantum mechanics. So this particular state, the 0 amplitude coherent state, it's actually called the quantum vacuum state as well. So we saw the quantum vacuum state before as the state, it's a photon number state with 0 photons, but it's also a coherent state with 0 amplitude. So the quantum vacuum state is kind of the limiting case of many different quantum states of light. It's a special one. Okay, so, oh yeah, and here I am showing, kind of schematically showing this 0 amplitude state. So it's not oscillating anymore, but it has some uncertainty. Okay, so let's go a bit more quantum. So we have the quantum vacuum state, and it has some quantum noise associated with it. But now I can do this operation, which is called squeezing. So, I mean, schematically, it just means we take this blob and squash it. And by doing so, what we end up with is a state of light that has less quantum noise in one axis and more quantum noise in the other. And this is actually a valid thing to do because, I mean, the quantum noise is related to the Heisenberg uncertainty principle, but the Heisenberg uncertainty principle doesn't put a limit on the uncertainty in each axis. It puts a limit on the product of the uncertainties. So as long as one of them gets increased, then we can actually decrease the uncertainty in the other one. And so this is this squeeze state that I kind of schematically showed as a squeezed toothpaste. And the reason the squeeze state is interesting is because you can actually use it to kind of go beyond the quantum limit, the quantum noise limit in metrology experiments. So there are proposals for taking, for example, the LIGO interferometer, and rather than having nothing go into one port of the interferometer, you can actually put in a squeeze state of light, which will make the interferometer even more sensitive. So this is like a super cool thing. Terrell, did you have another? I saw you got unmuted. Did you?
Yeah, I'm debating whether to ask a question and show my ignorance or not, but yeah. So the Heisenberg uncertainty principle basically says we can't know everything about it. We can't know everything about everything.
Well, it's kind of, okay, I don't want to,
In
like,
simple.
okay, here it just means like that the product, I mean, if this was like position and momentum, it would just be like the uncertainty in one, what's the word, property, and its conjugate property, the product of them has, some particular limit.
Okay.
I don't know if, yeah. Maybe yeah.
But I think it's interesting. So we can trade that off, not in a binary sense, because that's the model I have, where you need, everything about one aspect and nothing about the other. You're saying we can kind of manage that ratio there. It's not a 0 and 1, it's or all or nothing. It's,
exactly. Yeah, you can. And actually, okay, one thing that I didn't talk about here at all, but maybe I will, because I'll plug Xanadu. But if you infinitely squeeze these states, and in fact they don't even have to be infinitely squeezed, but in theory, if you infinitely squeeze them, these are the states that people use for continuous variable quantum computing. So if you've heard of this company Xanadu in Toronto, they're doing optical quantum computing. They actually use these states of light to build their quantum computer. And I guess the reason I'm bringing them up now is a couple of days ago, their quantum computer went, the cloud, they put it on the cloud. So you can actually now go and access this little tiny quantum computer made out of squeeze states. Okay.
Could you give, I mean, not to go off on a tangent, because I know nothing's simple here. How, from a quantum computing person's view, what does that add, or what does that take away from, what I'm used to, let's say, in an IBM experience? And if it's a long story, we can wait later.
Yeah, so I mean, at the moment it's like, so many of the hardware companies have software that then connects to all the different hardware as well. So at the moment, I don't think I can say that like one of them is necessarily better than the other. It's just they're all different, and we don't really understand everything about all of the systems. And so it's really cool to be able to play around, access all of these different systems, and learn new things about the actual physical systems. So it's not, it doesn't necessarily make it possible to do new simulations that you couldn't do elsewhere, but it's interesting more from the perspective that we need to learn more about these systems.
from deep down in the stack, and so, you know, as a algorithm developer, it's not bringing any special phenomena to the table
Well,
that we could take advantage of, at least that we know of yet.
I don't know.
You know,
Well,
like
I don't know.
a new gate
I
or
don't know.
yeah.
Yeah, I don't know. Maybe there is. But yeah, from a software developer perspective, I don't think I can answer that because I just don't know.
Well,
But maybe there is. Maybe there is.
something to investigate later.
Yeah. The other thing. So I mean, I don't know. At least, you know, from the articles that that I read, they have some plans to increase to double the number of qubits at a really, really fast rate. And so if that actually goes ahead, I think that would be pretty cool because, you know, soon the number of, well, they're called Q modes, but soon the number of Q modes might be quite large. So that might be an interesting thing in the future as well. But it's definitely, I mean, it's not something that's my area of expertise. So I don't really want to speak on behalf of.
Doesn't stop me. Anyway, thank you.
Yeah.
I have a question actually.
Yeah.
So what could be the applications of this quantum vacuum state? And once the number of photons increase in this bucket model, I mean, how could the superposition of photons be
Okay,
different
wait, can
from
we do one
superposition of
question at a time?
electrons?
Do I know you from LinkedIn? I think we were just recently exchanging some
right.
Yeah, okay.
Yeah.
Hi.
Yeah, hi.
So, okay, what was the first question?
Yeah, so what could be the applications of this quantum vacuum state that we're talking about?
Application of the quantum vacuum state.
Yeah.
Well, it just exists. So it's more interesting from the fact that it's kind of, I don't want to say liability. It's just something there that prevents us from doing certain things. Maybe there are kind of, there's something called quantum energy teleportation, and it's a protocol that lets you send energy from like one part of, you know, the world to the other, and that's
right.
like done traveling through the quantum vacuum. Also, I'm going to have like a mental blank now. But people are exploring entanglement in the vacuum. And in fact, what's interesting is that, okay, so like, let's say if you're trying to understand quantum gravity better, you know, we don't really have a theory of quantum gravity that everybody agrees upon. But people kind of try and study these aspects from, you know, looking at quantum field theory on curved spacetimes. And so I think in that field of research, people have kind of looked at how the quantum vacuum changes depending on the curvature of your spacetime. And so maybe if you have some detector that can somehow detect the energy of the quantum vacuum, it can tell you something about the curvature of spacetime. But again, this is not my area of expertise. It's just something, you know, I hear people talking about. So it could have applications in that sense. But mostly, I think it's just something that exists, and it is kind of a hindrance rather than a help.
All right, thank you.
Okay, and what's the other question?
Yeah, so the other question is, how is the superposition of photons different from that of superposition of electrons that we already have?
Oh, okay. So
I really apologize if my questions are a little bit silly because I'm from the quantum computing background, more towards the coding part and the machine learning part. So quantum optics is kind of new to me.
No, I think it's not silly at all. So electrons, they're fermions, and photons are bosons. So they have different statistics. And in practice, what this, you know, this has, you know, different things happen as a result of that. But the thing that's relevant here is that, so you can have two photons in the same quantum state, while you can't have two electrons in the same quantum state. So with electrons, you can have a superposition of an electron being here and here, or you know, maybe you can have superpositions of the electron being in different kinds of states, but you can't have a superposition of one electron and two electrons, because you can't even make a two electron state in the same way that we can do with the photons. Like you can't have like a ket with a 2 for an electron. You can only ever have like 0 or 1 electrons. So you kind of have this additional kind of freedom, which doesn't exist with electrons.
Thank you.
Okay.
Barry?
Yeah, just my question that I sort of blurted out in the chat.
Oh, I can't see the chat.
Oh.
So
We can squeeze this in any direction, right? This
yeah,
picture
yeah,
of
yeah.
no?
Yes, yes, you can squeeze it in any direction.
And is it more useful to do it in one direction than the other?
No, it's just important to know which direction you're doing it in, because
Okay.
yeah, that it's not. It's I mean, it's all relative anyway. The direction just needs to be defined with respect. So the direction, in some sense, it's a phase as well, because when you rotate it, you can define some angle. So that direction just needs to be fixed with respect to the phase of the other light in your interferometer. It's not really an absolute thing.
Right.
Okay.
One more quick one.
Yeah, sure.
So you said that two photons can be put into the same state.
Yes.
So the no cloning, is that cloning, but putting them in the same state?
Mm-mm.
No.
No. So let's see.
It's just their state. It's just.
I mean, there's nothing that prevents you from even, like, even if you had two electrons, and you had information encoded in those electrons, there's nothing that stops you from preparing two copies of the same state. You can do it. I'm going to prepare the plus state here, and I'll prepare the plus state here, and I've got two plus states. So that's not a violation of the no cloning theorem. The no cloning theorem tells you that if you have some state that's an unknown state, there's no operation that can then, there's no operation that when you bring in some other blank state and apply that operation on these two states, that you'll now end up with two copies of that original unknown state.
Oh, okay.
So in fact, you can even like if you know what that state is, like if you know that it's a plus state, you can make a copy of that. You just need to have a very specific operation that will copy the plus state. It's just that operation won't work on, won't let you copy different, like other arbitrary states.
Okay, got it.
And
Thanks.
what you're talking about here is the Pauli exclusion principle, that it doesn't apply to light? Or
Yeah, exactly. The Pauli exclusion principle applies to fermions, not to bosons. Yeah, that's a good point.
so
Yeah,
two pieces,
so then,
so whereas my two hands can't both be in the same place, if they were made out of light, they could.
exactly. Yeah. Which would be kind of cool, having hands made out of light.
Yeah. So two light can occupy the same space.
Yes. Yes.
Oh, and that's the waves interfering with one another.
Yeah, it's kind of, I'm sure it's related in some way. I don't know if it's exactly the same. I don't know if it's exactly a consequence of that, but for sure it'll be related in some way to
Okay.
that.
Maybe I'm simplifying it a little too much, but thanks.
Well, it's just things get kind of like when you're thinking about the particle picture, the photon picture, it's very strange to then like try and at the same time be thinking about the wave picture. It just gets very weird. So I don't want to just say, yeah, that's right, because I would need to think about it a lot.
Thank you. Yeah.
Yep. Okay, so let's move on. Okay, because so what have we seen? We've seen we have these two states of light, just the vacuum state and the squeezed state or squeezed vacuum state. But I showed you some other states as well. So I said there's something called a Schrodinger cat state and the photon number state. And you might be asking, well, can I draw these phase space diagrams for these states? And the answer is yes, but we need to kind of make the picture a little bit more complicated before we do that, because we can't just draw them as blobs anymore. So let's go 3D. So now what I'm plotting is here, this is now a two-dimensional function where the height represents the value of that function. And so to kind of connect it to this phase space picture I was showing before, if you just look from the top at, down the bottom, you'll see that here we've got this blip And it's a Gaussian or a normal distribution which has some some circumference, and that's what I'm representing here with this circle. And similarly for the squeeze state, it's some two-dimensional normal distribution where now it's squeezed along one axis, and that's what I was representing here. So you might be thinking, well, what actually am I plotting on the z-axis? What is this value? Well, this is this Wigner function that's supposed to be the main point of my of the talk. So this Wigner function is the thing that we is a very common object that we use in quantum optics to describe different states of light. So if you believe that, then we can dive right into the Wigner function, and I can tell you some more things about it. So, okay, so you probably know that, that in quantum mechanics, all quantum states can be represented by something known as a state vector. So this is this psi inside these two brackets. It's otherwise also known as a ket. And so any quantum state can have this description in principle. And that's the same in quantum optics. So for any quantum state of light, you can write down a ket for it. So you may have seen some examples in quantum information, like if you've seen these qubits, zeros or ones, these are just different kets or different state vectors. Schematically also I've been drawing this superposition of the alive cat and the dead cat. These are just quantum states. Okay, so if you want to figure out what the Wigner function is for some quantum state, you need to first write down what the state vector or the ket is. And so there's a recipe for getting from the ket to the Wigner function. It's a little bit involved, so I'm going to describe it to you because I want you to see what's happening, give you an idea for how this works. But don't worry if you don't understand each of the steps. It's not like that important. But anyway, I think it's fun to see. So you just need to go through a whole bunch of steps. You start off with the state vector. Then you write it as an outer product. So if you are familiar with the linear algebra, what this means is like I have a vector here, and then I write it as, I get a row vector and a column vector, multiply them together to get a matrix. Then I multiply this matrix by a special function, which I won't go into. Then I take the trace. So the linear algebra equivalent of that is that if I have my matrix, I just add up all of the diagonal elements. Then I take the Fourier transform, which is just another mathematical operation, and it spits out the Wigner function. And so I start off with this state vector. Here I end up with a function of two parameters, this x1 and x2, and then I can plot that. And so I actually have, like, if you want to see the mathematical version of this, I have a slide at the end where I can just like show you what the math looks like and what the Wigner function looks like, but we won't cover it at this point. So what I'm going to do is just like lump all of these different operations and just call it the Wigner function recipe. And so I put in my state and get out the Wigner function. So let's just see how this looks for some states. So we've seen the quantum vacuum. Let's put that in the Wigner function recipe, and we get out the Wigner function that you've already seen. So that checks out. Okay. What about for the single photon state? So let's pop that into the Wigner function recipe, and we get something that looks a little bit different. And so hopefully, you can kind of see why I was a bit hesitant to draw this on just the phase space picture, because we're starting to get some interesting features here. You can see it's kind of this donut shape. I'll talk about this later, but it actually dips below 0, which is interesting. Okay, what about a 5 photon number state? I'll put that in, and I get out something that looks like someone dropped a pebble inside a pond. It's got some interesting ripples there. So we're already starting to see that there are several different features for quantum states that are different or more interesting than we have for classical states, which are just a single point in the space. So I want to kind of change gears a little bit and have a little meta discussion about how physicists actually use Wigner functions before coming back to saying more about the Wigner functions. So I don't know if anybody wants to ask anything at this point before I or maybe actually a better place to ask a question is at the end of the meta discussion. But okay, so I wanted to say a few things about how physicists actually use Wigner functions. They use them for simulations, which is in some sense like the most kind of obvious and technical one. They use them to model the evolution of quantum states. They also just use them as a communication tool amongst researchers who are familiar with how to interpret Wigner functions. And they also use it to run thought experiments because it's really hard to imagine light, in your head. So having kind of the Wigner function as a tool helps. So I'll just go through each of these a little bit. So from the simulation perspective, you can just use the Wigner function recipe to figure out what your quantum state is. And then you can just evolve that Wigner function. You don't have to evolve the quantum state itself because we have equations that describe evolutions of Wigner functions. And so then you can evolve it and see, interesting things are happening over time and so on. So that's like one example of someone doing such a simulation. Yeah, I mean, physicists often use pictures also to communicate with each other. It's not just about the math. Often, when you become familiar with different kinds of diagrams, like Feynman diagrams or block sphere diagrams or Wigner function diagrams, it's just a really effective way to quickly communicate. You're trying to say something in words, it doesn't make sense, and then you're like, oh, just sketch the Wigner function, and then suddenly, people understand what you mean. So it's, in some sense, I feel like, I personally have never actually simulated Wigner functions, but I use them all the time in order to communicate ideas. So, amongst my colleagues, but also when I'm writing a paper, I, draw a Wigner function because I'm trying to communicate something quickly. And then, yeah, finally, it's kind of to run thought experiments and develop intuition in order to maybe make predictions about, if you're trying to generate one quantum state of light using, some other quantum state of light, it can help with that. So I will, I'll talk about that a little in more detail a bit later. Okay, so I was trying to kind of convince you that it's useful to know some intuition about the Wigner function. So what I'm going to do now is go through and highlight some interesting properties to help you build this intuition. So yeah, I am going to pause right now though to see if anybody has a question.
Hi, it's me again. I think I must have spaced out when you talked about what photon number is. There's 0 when there's no vacuum. Mm-hmm. But then what does 1, 2, 3, 4, and 5 mean?
It means that you have 1 photon or 2 photons or 3 photons.
That's it, huh?
In the same quantum state.
Okay.
Yeah. So what that physically means, I think you probably have as much of an idea as I do.
All right, yeah.
What I know is that I can represent things like that and use it to make predictions of experiments where people go and measure certain things.
Right. Okay.
Okay, I mean, it has, okay, it's, so how do I want to say it? So a photon has a particular, a specific amount, depending on the frequency, a photon is going to have a specific energy. And so you could have, let's say, some kind of detector that is sensitive to the amount of energy that it measures. And so if you take a quantum state of light that's like a 1 and send it into this detector, it's going to then give you a trace of some voltage or something, and it'll be like some height. And then if you send in a state that has 2 photons in it, it'll give you a different trace that'll be twice the height. And so it'll be a quantum state of light that has twice as much energy. And you can do this for many different photon number states, and you'll find that they all have discrete voltages or whatever it is that your device converts the energy into. So that's kind of one way to think about it. So there's Bill Unruh, the Unruh effect guy. He has this. Okay, so in quantum mechanics, people, or in quantum field theory, people argue a lot about what actually is a particle. And Bill Unruh says a particle is what a particle detector detects. And I think that's the same thing, you know, a photon is what a photon detector detects. We don't really know what a photon is. We just know that there are different states of light that if we send them into something we call a photodetector, it has different signatures that we identify with 1, 2, 3, 4. Like it's kind of, the energy is quantized.
Thank you.
Okay, that was a long answer, but.
Oh, this is quantum. Matthew, did you have a question? I had to unmute you or mute you. Did you unmute on purpose? Did you have a question, Matthew? If not, there's a no, okay. Shital has a point or question. The photon count in the buckets represents photons in the same state and point in space, right?
Oh man, I don't even want to talk about space.
I think that's a trick question because they knew it was gonna. They knew you were gonna trip you.
Yeah, no. Okay, so I'm looking at a really like idealized picture here, which is that I have a photon that is a single color. And if a photon is a single color, that means kind of if I look at the wave picture, it's a wave that goes on forever. So in this idealized picture, the photons I'm talking about actually like take up the entire universe. And so, yeah, they're both in the same space. But in reality, you know, photons aren't like that. In reality, photons have some frequency distribution, and then they have some time distribution as well. So they can be kind of localized wave packets, or they can be delocalized wave packets, but not, you know, completely across the universe. So in order to call it really, you know, a 2-photon bucket state, both of the photons would have to have exactly the same frequency distribution and exactly the same time distribution. Like the little pulses would have to be in the same place. But things get really weird when you talk about space and photons. So I was kind of trying to avoid that discussion. Because it's like, I mean, the reason it's weird is it completely goes against our intuition of what particles are. We think of particles as being these localized things that, you know, maybe, okay, electrons are a bit fuzzy, but they're still kind of localized in a particular place. But photons, they can, you know, they can be lots of weird shapes. If you have an atom that's excited and then it decays and it spits out a photon, that photon is going to go off in like one, you know, a wave in 3 directions and then go spread out across the universe. It's really weird to think about that as being a particle. It's like weird. So I don't know what else to say except that it's weird.
Yeah, so, I have a question.
Yeah.
So can we have many multi-photon number states interacting with each other? Like, for example, 3-photon state in one place and then 4-photon states in one place. They are kind of interacting with each other. Is that also possible?
Depends what you mean by interacting.
Okay.
So yeah, so I could, for example, let's say, so a common optical element that you have in quantum optics, or classical optics, is something called a beam splitter. So it's like a half-silvered mirror, and you know, if you sent a beam through it, it would reflect or transmit through. So you can, like the way that people often in quantum optics combine different quantum states of light is with a beam splitter. You can send some light in one port and some light into another one. So yeah, you could have like a 3-photon state and a 4-photon state, and they interfere on a beam splitter, and then they come out entangled in some like crazy superposition of, you know, 1, 2, 3, 4, up to 7 photon states. So they can interfere in that sense, or interact in that sense, if that's what you meant. But then there's another way that we combine them sometimes, which is as superpositions. So you can have a superposition of 3 and 4 photons. And, you know, in fact, most interesting quantum states of light are superpositions of different photon number states.
Awesome. And do the detectors also have to evolve with the increasing number of photon states?
Do they have to evolve?
Or we can use the same detector for, you know, different number of photon states that we have.
Oh, okay.
Yeah.
you would use the same detector. I mean, photon number detection is really hard. Like, I think it's only in the last 5 or so years that the detectors have been like really good. And I'm not going to remember the numbers, but it's something like this. Really good means that like it works with like 97% efficiency, and it can count up to like 10 photons or something like that. You know, maybe it's like a bit different than that, but it's not like they're perfect. So yeah, there are detectors that would count, you know, some handful number of photons, but I think once you start getting into really high photon numbers, it's quite difficult.
All right, thank you.
Okay, so, okay, yeah, let's talk a little bit about these Wigner functions, just to kind of, so the reason I wanted to say these things is because sometimes you see in papers, people show Wigner functions and they're trying to tell you something about it. So I wanted to highlight a few things. So one of them is this notion of phase. So I showed you before that, you know, the phase is like the angle on the sphere, sorry, on the phase space. So I want to compare the single photon state and the coherent state. And it's a little bit easier to see if we just look from the top down. So I'm just going to draw them here. And so here you can see, you know, the coherent state, you can draw a line from the axis to where the state is and define some phase. While for the single photon state, it's perfectly rotationally symmetric here. So you can rotate it around and it doesn't change anything. So there's not really any way that we can draw an axis and define a phase. So sometimes you hear people say something like photons don't have phase. And when they say that, that's what they mean, that the Wigner function doesn't let you define the phase. And so we can look at the 5 photon state, and as well you can see that it, you know, is rotationally symmetric. So none of the photon number states have phase. Okay, another thing I wanted to mention is this idea of negativity. So sometimes people try and make an analogy between the Wigner function and a probability distribution. And it kind of works for things like coherent states and squeeze states. But as soon as you start to get into the interesting states, you see that they go negative. And so, you know, you can no longer think about it as a probability distribution because, you know, probabilities can't be negative. So actually, well, let's look at it from the side. You can see, you know, for the coherent state, it doesn't dip at all below 0, but for the single photon state, you see this dip. And so this is a very hand-wavy thing. It's not, you know, very well defined, but it's something you hear people talk about a lot, saying that whenever you have a Wigner function that goes negative, you have a real quantum state, not just some, you know, Gaussian state. So you might see this talked about. Yeah, so you can think of this as quantum and that is classical. And same for, you know, the 5 photon state also goes below 0. Okay, and then another thing that's interesting is you can kind of think about kind of coherence or decoherence in terms of the Wigner function. So I could take like a classical mixture of, or a statistical mixture of 2 different coherent states, and the Wigner function for that would just be 2 different blobs on the same blob. But if I took a coherent superposition, you know, a quantum superposition of these 2 things, you find that you have these interference fringes in the middle that then go negative. And what happens is that as the, you know, you prepare this nice superposition state, but then it starts to interact with the environment. And the intuition that you can use is when it's interacting with its environment, the Wigner function is kind of shaking a little bit. And as it's shaking, it like washes out the rapidly changing positive and negative bits. And so they just, you know, wash out and average out to 0. And in the end, you have this classical mixture. So you can kind of use that to make predictions about how stable different coherent states are, different quantum states are. Okay. And maybe I will, so I think I'll skip over the last bit of the talk, which was going to be about how we make the quantum states, because I think it's going on for quite some time. But so finally, I will just tell you a little bit about how you can use the Wigner function to guide your intuition if you wanted to create some interesting states of light. So this Schrodinger cat state that I showed you, it's actually really difficult to make in practice. So it's worthwhile to think about how you would approximate it. So let's have a look at, I have a video here. So let's have a look at what happens if I kind of tweak some parameters for the cat state. So what's important is that, you can think of this as being the alive cat, that's the dead cat. And then these are the interference fringes. And the distance of these things from each other is related to the amplitude of the cat state. So if I now play this movie, I'm increasing the amplitude, so they're moving away, and the interference fringes are becoming more and more frequent. And now as I decrease the amplitude, they're coming closer together, the fringes are becoming more spread apart, and eventually, at some stage of, I pick an amplitude, I get a state that looks kind of like this. And you can see it looks a little bit similar to the single photon state, but not quite. So in order to get the states to be more similar, I have to apply a squeezing operation to the single photon state. So now I'm squeezing it a little bit and so on. And then we see that, well, we have two Wigner functions that are quite similar to each other. And it turns out that if two Wigner functions look the same, then the quantum fidelity between the Wigner functions is also very high. So they're almost exactly the same quantum state. And so what's interesting here is that even though making a Schrodinger cat state is really hard, making a squeezed single photon state is actually quite standard. Like you just need a nonlinear crystal, which is a routine element in quantum optics labs, and you need a single photon detector, and then you can conditionally create these states. So hopefully that gives you a sense of how you can use the Wigner function to gain some intuition. So yeah, here we have this, since it's a small amplitude cat state, it's usually called a Schrodinger kitten state, which is similar to the squeezed single photon state. And I could talk about the experiment, but I won't. So okay, maybe what I'll do is I will just like jump over these slides. And get to the end, which are the takeaway messages. So, I mean, one of the things that I wanted you to take away is that you can always build up this Wigner function picture by first starting off with something that you're probably familiar with, which is, that light is a wave, and it has a phase and an amplitude, which then I can plot as a phase space. And then if I add some quantum noise, I can already start thinking about quantum states. And we can use the Wigner function to develop some intuition, so we can understand whether quantum states have phase. The negativity tells us about the quantumness of the state, and also we can try and understand the fragility of coherence just based on how quickly oscillating the fringes are. And what I didn't talk about, but maybe I will if people ask about it, is that you can actually create all of these states of light that I was talking about just by different variations of the same experiment, which is where you take a laser beam that you shine on a nonlinear crystal, and then light comes out the other side. And so depending on how you set it up, you can make the squeezed vacuum state, or you can conditionally prepare these squeezed kitten states, or you can conditionally prepare these photon number states if you have detectors that can distinguish between the number of photons. So I'm going to wrap up here, and I will do that by saying thank you to all of you, and thanks to Terrell for being so kind to invite me here, and for being a very entertaining host, because I've been enjoying the chit chat. And yeah, I'm happy to like answer questions or have more chit chat if you guys like.
Well, thank you. Before breakfast, anybody have any non-space questions? You certainly gave me a lot to chew on here. This is another one of those talks where I'm going to have to watch it a few times. But the Wigner function, am I saying that right, Wigner?
Well,
Wagner?
I say Wigner. I mean, I don't know. I guess he was he Austrian? I guess. I don't know. I should know. That's terrible. But,
anyway, that function, that's a new vocabulary word for me. And
Yeah.
And have to do a
But you'll
dive
see
into
it
that.
all the time now. You'll see it
Yeah.
all the time now.
Yeah,
Yeah.
good. Thank you. I've probably seen it, it's that psychological thing, but is that function, I don't know why I'm asking where I'm going with this, but is it reversible? Is
Oh yeah, if you're given a Wigner function, can you figure out the quantum state?
yeah, and
Yeah.
I think the
Yeah,
answer
there'll
is
be-
yes, because that's why you can manipulate the Wagner function to imply a particular state.
Mhm.
Is
Yeah, there's definitely a one-to-one mapping.
my logic's
Oh, actually, so okay, okay, let me hold off on that. I could imagine plotting some function that does not represent a real quantum state. Now that I think about it. Okay, for any Wigner function that does represent a quantum state, there'll be a mapping back. But I think that there's some limit on how frequent the oscillations can be, I think. And so maybe you could cook up something that doesn't represent a quantum state.
it's kind of out of the bounds. Yeah, okay, but it's just kind of deterministic. It's a mapping.
Yeah,
It's a function, so therefore.
If it's a true Wigner function, there'll be a mapping.
Yeah.
And actually, one thing I wanted to add about the Wigner function, so all of this that I've been talking about is in the context of quantum optics, but the math translates to different quantum systems as well. So usually a mode of quantum light is what's known as a quantum harmonic oscillator. But the quantum harmonic oscillator exists, in lots of different areas of physics. So for example, if you had an electron that was inside a parabolic potential, so you've probably seen this in like undergrad textbooks, that you get these kind of wave functions that's like a Gaussian and then some kind of ripples. Like essentially you have your harmonic oscillator and then you have these lattice states. So that's a completely different physical system. But you can represent that kind of system with a Wigner function, where now the axes are literally position and momentum of the particle, while here the axes represent something a little bit more abstract. So you'll see the Wigner function outside of quantum optics as well.
Okay, cool. Saeed, you get something out there? I could see you.
Yeah, actually,
up a question.
One of the great applications of quantum computers to understand how the universe works, to uncover the mysteries, right? So can quantum optics help us in understanding dark matter in any way? I mean, is there any research going on in this field?
Yeah. Okay. So here's my crazy proposal. So, which I tried pitching to the particle physicists at Permina, and they kind of
I would love to hear that.
Listen and then dismissed me. Like, okay, go play with your light. But yeah, so my crazy proposal is to send cat states between satellites, and if they interact with dark matter particles in some way, it would decohere the light in a special way, and you'll be able to somehow detect them. The problem is that most dark matter, we don't really know what dark matter is, but most of the candidates don't interact with light because it's dark. So the reason we can't see it is because it doesn't interact with light. So I think there's only one particular dark matter candidate called an axion, maybe, but maybe there's some potential that you could use it this way. But that's completely different to what you were saying, because you're talking about quantum computing, while I'm talking about physically trying to detect the dark matter with light. Now, in terms of quantum computing, I don't really, okay, so one way in principle a quantum computer could help you understand dark matter maybe is if it's powerful enough to simulate some kind of new theory and make predictions that you couldn't do on a classical computer. But then I don't think necessarily a quantum computer made out of light would be there'd be any fundamental reason why that would be better at solving that problem than any other quantum computer. It's like whatever quantum computer you end up with, that's the best one, that'll do it. But I don't actually know, do you know, have there been proposals for using quantum computers to solve, to simulate those specific problems?
Yeah.
I don't know.
No, I haven't come across such a thing. So
yeah, I think it's
wanted
interesting.
to know your, yeah.
Yeah.
Mm-hmm. And if possible, can you talk about some parts of research that is happening in University of Waterloo in
Talk
the
about
field
some
of
parts of
quantum
research.
optics.
That's a really broad question.
Yeah,
Okay.
in the field of quantum optics or application of quantum optics, especially in the field
Yeah,
of
so I mean,
numerical
Kevin
processing.
Ratch, he's got an experimental group there. So he does a lot of really interesting quantum nonlinear optics. He does some cool, I mean, they're coming up with new techniques for measuring quantum light, also techniques for converting quantum light. So it's very difficult again, we have techniques for changing red light into blue light, for example, classically. But if you want to do that efficiently for a single photon, it's really difficult to do that. So their group is working on things like that. They also so they collaborate with Perimeter Institute quantum foundations theorists. So Rob Speckens, for example, proposed some experiments for them to do on something called quantum causal models or something like that. Things like trying to understand whether you can have, okay, so causal order is like, A influences B or B influences A. So they're looking at, can you have superpositions of A influencing B and B influencing A, and what does that even mean? So in Kevin's group, they were doing some experiments studying that. The other quantum optics stuff is happening with Thomas Genowine's group. So they focus on, well, one of the things they focus on is trying to do quantum cryptography between the ground and satellites. So they have like a whole bunch of funding now to send QKD to satellites, which is like pretty cool. And also we're exploring with that group, we're looking at different kinds of analog experiments. Like maybe you can think about, can you model how light bends under the influence of gravity? Can you maybe model that in some sort of quantum optics experiment? So we're kind of playing around with those things as well. Yeah, that's off the top of my head. I'm sure there are other things, but off the top of my head, that's mostly what's going on there.
Thank you. It has been a wonderful talk. It would be really appreciated if you could share, a few resources to get started in the field of quantum optics.
Share some
Considering
resources?
a person is, yeah.
Yeah, so I think the best resource to start with is a Coursera course called Quantum Optics 1 and 2 by Alan Aspect. So he's an experimentalist in France, and he's one of the people that did, I think, the original Bell experiments decades ago. It's such a fun course, and it really covers everything that you need to do. So I would recommend that. And then I think one of the more introductory quantum optics textbooks, which I think is a good place to start, is Peter Knight's book, Knight and Jerry. They have a quantum optics book as well. Do you want, I can just, on LinkedIn, I can just send you what they are, or I can share them on the chat.
Yeah, that would be awesome. That would be awesome.
Maybe I don't know if I can, I don't know how to get the chat. Anyway, I can, oh no, there's on the Meetup. I can post on the Meetup thing. I'll post the link so other people can see them too if they want.
That'd be cool.
Yeah, sure.
I think I found the Coursera link.
Okay.
Yep.
Quantum optics, single photon.
Yeah.
Look like,
and then I think quantum optics 2 is more than one photon.
I get it.
Awesome.
I get it.
Yeah.
All right, cool.
Yeah. Thank you.
Anybody else? Last chance, as long as it doesn't involve something with space.
Actually, can I stop sharing my screen? I feel so...
I think you did. Oh, no. Yeah. Okay. Yeah. There you go. All right. Well, thank you. But let me take this opportunity. I'm going to announce I've got a series coming up, and I'm going to announce it just simply because the first speaker in this series is from University of Waterloo.
Oh, who's that?
And I forget who it is right now. I'd have to check my notes to be honest with you, but well, I can do that right now. Hold on. Let me see. Waterloo. Anyway, it's a series of master's degree programs globally, where I've made contact with practically. It's let me see. It'll probably be John Donahue.
Oh yeah, no, I know John. Yeah, he's great.
Yeah,
He's a quantum optics guy as well. He now is more on the outreach side, but he has a PhD in quantum optics, and he's like a super bright guy.
Yeah, so he, anyway, so it's a series of quantum master's degrees around the world where I've invited each of the program directors of the various universities globally to come give a talk during October. The first one's October 1st, and I'll publish it in a minute or two.
Are you going to call it Oktoberfest?
Say again?
Oktoberfest?
I didn't think of that. I call it Quantum Masters. I couldn't be more, you know, I couldn't get as creative as Quantum-a-Palooza on this one. But
October Masters Fest.
But it could be, yeah, you know what, next year I'm going to think about that. That's right. It is October. Yeah, because I hope it'll be an annual series. But each of the program directors over the course of the month on Tuesdays and Thursdays at different times, because I want to get the different time zones, will come and talk for about 20-30 minutes, you know, introducing the world to their program, their quantum program, and some of them are optics, master's degrees, and then talk about their university and stuff like that. So, you know, not all of you are interested in master's degrees, but if you have friends who you know, would like to get into quantum or, you know, want to get a degree in it, this would be a great resource to go to. I also, not to continue on the advertising because I'm not a big fan of advertisements, but if anybody...
It's good. You're sharing things that people want to know about.
Well, yeah, it is. Yeah, I'm not selling anything, but it is for the community. And let me add one more link here, if I may, for you folks to take up some of the airtime here. And this is a site where all the information will come out. I just put it in there.
Oh, yeah.
Anyway, so, but I just bring it up because Waterloo is the first one.
Cool.
They'll open the show on October 1st. So
yeah, you should go to John's thing. He's great.
Yeah, and for the learner, even if you don't want to, you know, you're not planning on a master's degree or you don't have any friends, I think it's you know, if you want to get to know the industry and the ecosystem, this is a great opportunity because, you know, in setting this up over the past N number of months, I found every program is different. They have different strategies. They have different, you know, they're going after different types of people. And I think it's just a really good opportunity to get a sense of what it's like in that part of the ecosystem, because they're very different and they have different, you know, not only the technologies that they're focused in on, some are focused on engineering, others are focused on the, you know, the basic science aspects of it and so on. So I think it'll just be a good educational experience, you know, to have all these, it's like a buffet of educational things. So anyway,
yeah,
I drone on. Aggie, thank you very much. I appreciate your flexibility and your, you know, you can come to this party anytime you'd like.
Yeah, cool.
Absolutely, and appreciate handling the questions and for those of you who are here tonight, let's get some rest, and the others go get breakfast. Thank you very much, everybody. We'll see you all.
Thank you so much, Kyle. Thanks, everyone else.
Cheers. Bye-bye.
Thank you, everyone. Bye-bye.